Morning is John Hitchcock from Wyoming University. Let me get away there. Okay, thank you very much.
Thank you. So I'm going to talk a little bit about reducibility to the set of Kolmogorov random strings. So I'll give a little bit of background on the topic, mention some of the previous results. This is a topic that started out in computability theory, where of course the reductions were not resource bounded, and it's grown into computational complexity theory, where we've mostly looked at polynomial time reductions of different kinds and have found interesting connections with topics like de-randomization and pseudo-randomness. And I'm not going to mention all of the work that's been done, just to highlight a few things and just kind of give a taste of a few recent results I have, and highlight some open problems that I think are interesting and appear tractable to me, but a little bit beyond the scope of what's been done, or at least that I know how to do. The basic idea here is RC is the set of all binary strings that have Kolmogorov complexity at least their length. Now, as soon as you start to talk about something like that, you may have a few quibbles, because there's a few choices that you could make in defining that. Do you talk about plain or prefix-free complexity, for example? The answer is that, well, sometimes it does matter which one you use, but for most of what I'm going to talk about, it doesn't really matter. For many of the applications in complexity theory, it doesn't make a difference really if you use plain or prefix-free complexity, or if you say, C of x is strictly bigger than the length of x, or if you put greater than or equal to there, or if you change that by some constant factor, or if you change the randomness threshold by something more dramatic, by the length over 2, or put it by something polynomially related, by say square root of the length, or there's lots of ways you can vary it. And for complexity theory, all these things are going to have roughly the same computational properties. Now, it's not always the case that these sets will be computationally equivalent. It depends on the particular application. So you have to be careful, especially when you're looking at these sets in a computability theoretic setting. Anyway, I'll say RC pretty much exclusively throughout the talk. if I accidentally wrote RK somewhere, I probably meant RC, and if I don't know. So, yeah.
Comment.
Yeah.
So this finite strings in this, in this dichotomy that Sasha likes very much to point out. But I mean, it is an infinite string. I mean, so do you think that techniques are more like from finite string Kolmogorov complexity, or more from randomness, or nothing to do with either of those? I mean, the techniques to deal with this set. I can ask later.
Well, I mean, we're talking about it, instead of finite strings, but to study reducibility of the set, I'm going to, toss in techniques from resource-bounded randomness, like polynomial time dimension and stuff like that. So it's kind of all connected together in my mind. And another thing that matters, of course, is that if you vary the choice of universal machine that you use to define complexity, you're going to get a different set of random strings. And, it's not going to change what's random a whole lot, but it's going to change the set somehow. And, it's not going to change whether it's complete or not, or whatever, but it's going to change what the set is. So most of the time we don't have to worry about that, but sometimes we will need to be specific about what machine we are actually using, and so then I'll explicitly write what machine I'm using in the subscript for the complexity, and have a double subscript there, RCU. Okay, so of course this is a complex set. I mean, it's undecidable because Kolmogorov complexity is not computable, and in fact it's very useful as an oracle. It's hard for the CE sets under Turing reductions. And sort of the starting point for all these investigations was Kummer's theorem in the mid-90s. A very surprising result. Showed that something much stronger than you get from Arslano's completeness criterion, that instead of just a Turing reduction or a WTT reduction, you get a conjunctive truth table reduction to the random strings. Or equivalently, the way I like to think about it, a disjunctive truth table reduction from the complement of the halting problem. So throughout the majority of the talk, I'll actually be talking quite a bit about disjunctive truth table reductions. So a disjunctive reduction, as a reminder, is just where you take an instance of the first problem and you output a list of queries about a second problem, such that the first instance is positive if and only if at least one of the queries is a positive instance of the second problem. No, I don't think so, because I flipped the reduction.
But it should be done in the theorem.
Did I write something wrong here? Yeah. Yeah. Yeah, conjunctive is and all of the queries are in the oracle set. Disjunctive is an or. Yeah. So.
Somewhere we need
Um,
Oh, yeah, then you're right. That's right. That's what you got there, correct. That's correct.
So anyway, here you have these, a couple different reductions to the random strings. But if you look at the proofs, there's no efficiency guarantee whatsoever. And Allender and his co-authors in a series of papers, and I think even one of them is named this maybe, asked what can we efficiently reduce to the set of random strings. So now Kummer's result does imply that there's some time bound. So, some t of n such that if you look at any decidable, I'm going to focus on decidable sets, I guess, because or even sets lower than that, because I'm a complexity theorist. But there's a time bound from the from the confluent of the Halpling problem, such that you have a disjunctive truth table reduction. But the proof is not constructive, and it doesn't really tell you what t of n is. And Allender and his co-authors, actually, later on I'll say who all the co-authors are. They show that that there's a reason for that. The t of n, the time bound, actually depends on the choice of the universal machine that's used to define the Kolmogorov complexity. So it's kind of interesting, I think. So however large a time bound you want to take, you can find some universal machine so that it takes at least that much time to give this DTT reduction. So this is kind of something undesirable, maybe. So what's the next thing here? So this is sort of the flip side of the coin. There are also sets of very high time complexity that are still decidable, yet they polynomial time disjunctive reduce to these sets of random strings, regardless of what universal machine you happen to be using. So you look at these results about disjunctive truth table reducibility to random strings, and it starts to raise some questions. And so I'm not going to bore you with lots of slides about notation. So here I'm using p dtt of RC for the class of problems that polynomial time disjunctive truth table reduced to RC. So it's that closure of sets that reduce to RC under that class of polynomial time reductions. So independent of U, that class contains sets of very high time complexity. However, if you look at the proof of their theorem, you'll see that the these sets of high time complexity that they're constructing are very simple in some other senses, as in they're constructed using kind of padding techniques. They're these like super tally sets, and so they're very sparse. And so in some other ways, they're kind of simple. And so, those kind of sets are certainly, dimension 0 classically, and effectively at any level you want. And indeed, what I'll show you is that anything in that class, not just the sets that they construct, but anything in there has a polynomial time dimension 0. So as a corollary, we get that the set of random strings is not polynomial time disjunctive hard for exponential time. So this is a lower bound. So here E is the class of problems that can be decided in 2 to the order n time. So 2 to the Cn time for some constant C. The idea behind this investigation is to kind of see what can and cannot be efficiently reduced to the set of random strings under what types of reductions. And so here we've got a complexity class that cannot be disjunctively reduced to RC under polynomial time reductions. You would think you could push that further up than E, but it's a start.
Can you say how the corollary follows?
Oh, yeah. And I'll get into that a little bit more when I do the proof. But basically, it's because E has P dimension 1. So this class has P dimension 0. And so it cannot contain a class that has P dimension 1. And so that's an unconditional result. You can't hope to prove unconditionally that the random strings are not NP hard, because you'd separate P from NP. So, but we can do the next best thing and prove that they are not NP hard unless P equals NP. And so that follows actually from the same line of investigation that gives the result in the previous slide. So I think this nicely complements the results of Allender et al. So, while I mentioned that they'd shown that you can find these arbitrarily complex sets that DTT reduce to certain RCUs, they also showed that if you take the intersection over all universal machines of the polynomial time disjunctive closures of RCU and restrict that to the decidable sets only, then that's a kind of an unusual definition of the class P polynomial time. So, while for individual U's there are some complex weird sets in there, if you kind of factor out over all universal machines, all that's left is just P. So, what these two results about E and NP show is that while for an individual U, those classes can have complex sets, they're still close to P for every U, because I didn't state the two results for NP and E. They hold for every RCU, so they still have small dimension and they cannot contain NP unless P equals NP. So these classes are very, very close to P, even though they have high complexity in other senses. So I'll these results for E and NP, I'll kind of sketch the proofs briefly. I just want to mention some other results that I won't really go into details about. So beyond disjunctive truth table reductions, it's also very interesting to look at more general Turing and truth table reductions. So there's who Allender et al. It's Allender, Berman, Kuchke, Van Mikkelbeek, and Ronneberger. So using quite a variety of techniques from complexity theory showed that the random strings are hard for P space under polynomial time Turing reductions, adaptive reductions. I don't really have time to go into how that's proved, but very, very interesting result. And so when you have a upper bound like that, it's interesting to consider how tight that is, and can you prove some kind of lower bounds. You wouldn't expect to be able to get something like that with fewer than a polynomial number of queries, maybe. So what can we prove if we look at less than a polynomial number of Turing queries? So I've looked into that type of thing. Analogously for truth table reductions, more recently, Berman, Fortnow, Kuchke, and Loff showed that you can use the random strings to solve BPP with a polynomial time truth table reduction. So a non-adaptive reduction suffices in that case. So BPP is contained in P space. We think that that's a proper inclusion, but of course in complexity theory we don't know how to prove such things. So that's kind of the lay of the land there. Regarding Turing and truth table reductions, Allender et al. Had already showed for double exponential time, so this is where you're looking at a time bound of the order 2 to the 2 to the n, that if you considered a sublinear number of truth table queries, so see here I've switched to RK, and I don't know when I switched. Oh, just now. But it doesn't matter. It's RC. Anyway, a sublinear number of truth table queries does not suffice to reduce to the random strings. So here we're looking at n to the alpha queries where alpha is less than 1. And that was proved kind of using just a direct diagonalization counting argument. Using polynomial time dimension and technique based on Winnow algorithm from computational learning theory that I developed earlier for reductions to sparse and non-dense sets. I was able to step that down a level to the class E, so just on the level of time 2 to the n rather than 2 to the 2 to the n. And get the analogous result. So get the separation, and in fact the way it's proved is by showing that this class of sets that reduce to RK by n to the alpha truth table reductions has p dimension 0. Now the situation for Turing reductions, adaptive reductions, is similar but a little bit more interesting. The proof that I was able to come up with there only works up to a little less than square root of n queries. So I would conjecture that that could also be pushed up to sublinear, but I so far don't know how to do that. So that's one of the open problems I'll mention toward the end of the talk. For these types of reductions, there are also results for NP, which again have to be conditional, or else we'd separate complexity classes. And so these results are based on the non-collapse of the polynomial time hierarchy. So you get the same type of non-hardness results. The random strings are not hard for NP under sublinear query truth table reductions. Unless the most precise statement is NP is contained in co-NP/poly. I don't know how to do it with just P equals NP. That would be a very interesting improvement. I don't know if something like that would be possible. And for sort of the same combinatorial reasons, for Turing reductions, the result also goes up to just a little less than square root of n. And so this is also based on techniques that came out of investigations into reductions to sparse sets. So it's kind of interesting in complexity theory, reductions to sparse sets going all the way back to the Berman-Hartmanis isomorphism conjecture and Mahaney's theorem and all that stuff in the late 70s and 80s. Techniques from that are useful for looking at reductions to RK. And you actually see why when we get into this proof here. This is kind of about the simplest proof I can show you. That's why I'm going to do it. The reason is that if you do a efficient reduction to the random strings, a polynomial time reduction to it, you're not able to output very many queries. And, well, it depends on what type of reduction it is, at least. But if it's not a very powerful kind of reduction, then you're not able to make, very much use of the oracle. So in some sense, you're only able to use a sparse part of the oracle. And so you can effectively replace it with a sparse set and use techniques from the reductions to sparse sets line of work. So, so let me try to sketch this proof. It's the only proof that I'll do in detail. So suppose we have a decidable set A that polynomial time disjunctively reduces to the random strings. I want to argue that it also polynomial time disjunctive reduces to some tally set. So, a tally set is just a subset of 0 star. So this is based on a proof technique of Allender et al., where they actually prove something more sophisticated about monotone truth table reductions to the random strings, implies a set has polynomial size circuits. And you can take their idea. Here we have a stronger reduction. A disjunctive reduction is a monotone reduction, and we'll get something much stronger than a polynomial size circuit. We'll get a tally set. Okay, so let's say the reduction is computable in time n to the d, and call the set of queries on input x q of x. And I'm going to let float for now some constant c, and L of n is going to be the query length for the length of queries that matter, in quotes. So the queries up to length c log n are the only ones that matter. So we're just going to use this in our argument while we sketch it, and we'll figure out what c needs to be later. But the idea when you're working through this, you sort of know that that's it can only be that long for this to work. You can only grab up to a logarithmic length, so that the total quantity of those strings is a polynomial number. So we'll do this and hope that it works. Okay, so I should put some pause commands in here so I don't throw this all up at once. But okay, so so at the top, x is in A means that there is a q of x intersects the random strings. And then define q prime to be q intersected with, basically q restricted to the queries that matter, restricted to length at most L of n. And then here's the key claim. You can think of this as we're it's sort of like you're looking at kind of equivalence classes. So it's saying that for every x in the set A, there's a safe short query Q so that if you look at any other y of the same length, if this safe query belongs to its Q prime set, that implies y is also in A. So notice here we aren't saying anything about whether this safe query Q belongs to RC or not. We're just saying it's in Q prime at this point. So if you don't have this, the idea is, as is usual in a proof like this, you could search for one and violate some Kolmogorov complexity consideration. So if there is some x that violates this, go out and look for the first one that does not have that property. So every query in its Q prime set belongs to Q prime of y for some y it's not in A. And so here's where we're using the fact that A is a decidable set. This is going to give us that this is going to give us a collection of non-random strings in Q prime of x is what that accomplishes. Now, on the other hand, x is in A by assumption. So by the property of the disjunctive reduction, Q of x has to have something in RC. But we just saw that Q prime of x doesn't. So there's a random string in there. And it's fairly long. It's longer than length L of n, our query length that matters. And so we're able to describe this string R by just describing n and this this search process, and then basically the index of that string within Q of x. And the time to compute the reduction we said was n to the d. So the size of Q of x is at most n to the d. And so anyway, you can describe this random string R that we've identified here in something like order log n bits, say d plus 3 log n bits precisely if you work it out. So let's just take that constant c that we needed to figure out to be one more than that, d plus 4. And that will give us the contradiction that we need. So anyway, that's enough to establish this claim. So to wrap up, what we have then is that only the short queries matter for this reduction. I mean, some of the, I guess it's possible, hypothetically, maybe some of the, probably not. Anyway, in the first line I should have written x is an A if and only if q prime of x intersect RC is non-empty. That's what we proved. So to code things into a tally set, here's the technical details. I don't think I'll worry about that too much, but you just pair things up by length using some pairing function on the natural numbers. Because there's only a polynomial number of queries to concern yourself with at each length, this will work. You can fold things together nicely, and you just have to adjust the reduction to output these tally strings instead of what it was outputting before. But that gives you the result. So that's the theorem. If a set's decidable, polynomial time disjunctive reduces the random strings, then it reduces by the same kind of reduction to a tally set. So as a corollary of that, get that if P is not NP, then NP cannot polynomial time disjunctive reduce to the random strings. And this follows quickly from a known result. If NP did reduce by that kind of reduction to the random strings, then that would mean that SAT reduced to a tally set by disjunctive reduction. Which would mean that the complement of SAT conjunctively reduces to a tally set, and an old result of Yukonin shows that P equals NP if co-NP has a sparse conjunctively hard set. So there's a conditional non-hardness result for the random strings for NP. Now for E, we can get the unconditional result, and you can do this a couple different ways. Go through P dimension is a simple way. So the class of problems that polynomial time disjunctive reduce to the random strings that are decidable is a P dimension 0 class. And so this just follows from previous work, because we now know that those are things that reduce to sparse sets, and that's been shown to be dimension 0. And so, as I described earlier, that means that E cannot reduce to the random strings. Okay, so now the open problems that I promised. have time to get into these results, I do want to highlight the gap between them. So for truth table reductions, we have a lower bound all the way up to sublinear, and for Turing reductions it goes just up to end of the 1/2. And it seemed like maybe you could also push the lower bound for Turing reductions up to sublinear. There was a situation like that for analogous situation like that for reductions to non-dense sets, sparse sets. That was open for a while. So it would be interesting to see that resolved. And there are a few different variations of it that you could formulate. Here are a couple. The one for E, something unconditional. Even that with exp would be interesting to see. And something for NP under some kind of hypothesis. It could be NP is not in co-NP/poly, or some other version of the polynomial time hierarchy does not collapse. Anything that somebody wants to come up with, I would be glad to see. So this is one that I've thought about off and on for a while. Whether every decidable problem is polynomial time Turing reducible to RC. So, we know that P space is contained in this class. And I don't know. Seems to be a lot that's left to be discovered about this. And my gut feeling about it is that this could be a right way to attack it. Showing this class the decidable problems that polynomial time Turing reduce the random strings has P space major 0, or equivalently doesn't have P space random problems, might be a good way to go about things. And lastly, this is a little bit more open-ended, but from the results that I've described, we know that, say, the satisfiability problem, the standard NP-complete problem, disjunctively reduces to the random strings. Without giving any time bound on the reduction. Kummer's theorem or whatever. And showed you a proof that polynomial time disjunctive reduces to the random strings if and only if P is equal to NP. So now there's to me, like a lot of a big gap between there. And so this question is a little bit more open-ended, but what more can we say about the amount of time that reduction takes? How much time does it take to disjunctively reduce the satisfiability problem to the random strings? Thank you.
Sorry, I was sharing. I forgot. Any questions?
Yes, so there is a question. Imagine we have an oracle which computes complexity up to a constant fact. Just if we try to get rid of this dependence, just make a weak assumption that there is an oracle which gives us the value of complexity up to an additive constant.
Okay.
So is it possible to reduce something polynomially? So how does any of your results somehow, positive results, extend to this case? Just theoretically, one can imagine that some very subtle behavior in this constant range is responsible for the effect, or it's something more robust.
Yeah, I'd have to think about it. So
Actually, so some of the early results actually, like the upper bounds actually do work basically. They are very robust. So they actually don't care about, I mean, they can take basically any approximation to Kolmogorov randomness and then they will work.
yeah, so it'd be sort of like answering a promise problem. Like if it's above, it'll say if it's so far above, it'll say yes. If it's so far below, it'll say no. If it's in some region around, it'll say it could say either way. Yeah, something like that. Yeah, then
it's a bit even a bit weaker than that, because then we just not if we maybe we could measure the complexity of any string independent of length, or we can just be in this.
Yeah. Yeah, that would, I think, would suffice for some of the positive results. But I'd have to think about it.
Any question? I had a small question. When you had that question there, in that open problem, the first one, I mean, how far is this RC from, I don't know, Martin law? Because of course this reminds me of this almost R classes, like almost P is VPP and it's P of a random or accord intersection with the decision with black decidable problems. So, any intuition? I mean, is this problem? Could it have any relationship with the fact that, of course, VPP has the space measures zero, or is completely unrelated?
So you mean, how does this connect with almost classes? Or
I don't know. If intuitively for you see any, any similarity of RC with and Martin-Love random language, because of course with the Martin-Love language, in the place of RC, if you have a Martin-Love language, that means VPP has the space measure zero, which is true, of course. So, do you think this is connected at all, or the power of RC should be far more than?
Even intuitively, it's much more different because then we have one element. In Martin-Love case, we have just one random element.
Yeah, and here RC is.
And here we have the possibility to distinguish between random and non-random. So
Yeah,
philosophically,
but
it looks a bit different.
Yeah,
But
you're right. But somehow in Martin-Love you have like infinitely many prefixes that you could use.
Okay, but just this will be correspond to what can we do if we, as an oracle, have one string. Here we have something.
I see. So you mean that in Martin-Love you only have one candidate per each length, whereas here you can.
No, it's just.
So you think this is
superficial?
So RC is more powerful in principle? Is that?
I'm not even sure what you mean by Martin-Love, because
the thing is that when you look at resource-bounded stuff, it's going to be different. I mean, when we say omega, for example, we mean omega, we don't really mean omega, we mean omega at the solid reducibility, or the initial segments thereof.
No, I mean,
but the universal machine will make a difference then
yeah.
for resource-bounded stuff, in the same way as it does for C.
Yeah, but it is known that if in that there, instead of RC, you add any Markov random walker, you get VPP. Okay, the VPP, the class VPP. Because it's P of any Markov random. That's what I meant.
All right. Okay.
So in that sense, omega would do, any omega would do for any universal machine.
Right.
But it's probably a stupid question.
Sasha already hinted at, if you look at it, this almost classes solved, then everything is rather natural, you just do the thing you would expect. If you look at the things here, the techniques, they are weird, yeah. So superficially, if you look at the techniques, it's completely different, yeah. But that does not look so related, yeah.
Thank you. So, any more questions? Okay, let's thank our speaker.